Hello, everybody.
Hi, Dr. T.
How we doing? How we doing?
Just having dinner.
Good. Dinner is good. Dinner is a very good thing. So let's see. How do I share my screen here? Hey, Pauline.
Hi, Dr. T.
Let's see here. I am trying to get to a good place. So I just added some stuff to the Canvas page. We have a least squares problem to do, and basically I'm giving you the data, and you can do a small subset of what I did, and I'll show you that. And that's here, and I'll make an assignment for it too. And then also there's our next paper, SIRS of problematic molecules. So we'll do this, and so let's jump right in.
Dr. Taylor, you're like 2 minutes early.
Oh, shoot. Sorry, that's a good idea. I should not jump in yet. I am too early. Thank you. Here we go. This is good. This one. This one. Oh. There should also be. Oh. How was that? There we go. So let's see. And Roger, Calvin, Kai, Adam, Kenya, Aditya, Lily. Here we go. There's Hikun, Carla, and Leslie. All right. I think we are all represented here. Excellent. Excellent. And I can see Calvin yawning, and I can see Dan amidst the pillars of something or other there, right? What are those, the pillars of creation? They call them the pillars of creation, right?
Really, I thought it might be the Horse Nebula too. Kind of looks like it.
Right, the Horse Nebula, right. And Adam is in his gaming room, which it's actually his living room, but it's also his gaming room. And Aditya is here in his dark room. And oh, wait, we're missing Richard, right? Okay, well, he can catch up when he gets here. Hi, Kenya. Hi, Kai. Hi, Pauline. Hi, Carla. Hi, Hikun. Hi, Leslie. So, oh wait, no, that's just us. Thank you, Hikun. So I promised to show you what I mean by there's Richard. What I mean by the fact that estimates in the parameters are, they form a parabola. Hey, Richard. Didn't miss anything, don't worry. the estimates and the parameters make a residual squared error function that is itself a parabola, right? And so what I have here is some data in the blue dots, right? And then I have a black line that obeys a certain b value, certain intercept value, right? And then a certain slope value, right? So the slope will change things without changing the intercept. And you can see that as I increment and decrement these things, the first thing that happens is that the fit gets worse, right? Like you would never accept this as the best fit line to these data points because it's above all these guys, right? And so this guy squared plus this guy squared plus that one's pretty much 0, plus this guy squared plus this guy squared plus this guy squared. All those squares summed up equals about 16 here, 15.5, right? So this is 13.65. That's 15.65. So this chord here, this blue line is about 2 long, right? 2 squared is about 4. So we've got 4 plus, maybe 3 plus 4 plus 4 plus, maybe 6 or something here, We add up all those values and we get to this value here that's seen on this graph of chi-squared versus b. Then as we change b, we kind of come down that guy, then we go back up when we get too low. That makes sense? And the m dimension here, I made this thing, but I don't actually know how it works. So it's a little bit too perfect. Because when you change b, the blob on the m dimension doesn't change, right? So how did I do that? I don't even know. I think it's sort of artificial here, right? But if you make the slope too low, then chi-squared goes up. Then if you make the slope just about right, then chi-squared is a minimum. And if you make the slope too high, then chi-squared goes up again. Does that make sense, everybody? Is any questions about that? No? Okay, cool.
Question.
So, yes.
Is this what we're doing on the Excel sheet that is our assignment?
No. The Excel sheet that is our assignment is right here. And this is uploaded onto Canvas. And this has the wave numbers and intensities for acetone, toluene, ethyl acetate, and a mixture of these 3 guys, right? And I want you to put your name here and then label these 3 columns and then do the linest, put the linest here, then answer these questions. What does the sum mean? You're going to take the sum of these 3 here. And then you're going to answer what's in this row. That's important. Then when you do the linest, you've got to supply y data, x data. You've got to answer 2 Booleans. One says constant, and the other one says statistics. And I want you to sort of write me a sentence about what each of these is. Then make a plot of the mixture, and then the model components here. Then make a sum of the components here, make the residuals, which will be the sum minus the mixture, make a square of that value and sum that column to make chi-squareds, then answer what it means to have perfectly random residuals, and then make a plot of the mixture and the model sum here, and make a plot of the residuals below. So this is a little bit too early to show you this, right? Because you're probably going to have some questions now on this one, right? Because this is basically what I'm asking you to do with plus some other junk, right? And so this is the data I gave you. And then this is the linast, right? It's got y's, x's, a false for constant, and a true for statistics. The y data, right, this first one here. By the way, can you guys all see this? Is this more or less legible? Okay.
Yes.
Okay. Yeah, I'm sorry if it's a little bit small, but the y data are the data to which we are fitting the sum of the x data, right? So what we're saying is that this number here, 4.8, is going to equal some number times this, plus some number times this, plus some number times this. And this number 68 will equal the acetone coefficient, the same number, times this, plus toluene coefficient times this, plus ethyl acetate coefficient times this, right? So basically, we get three coefficients out, right? Like acetone is 50.9%. So this is the number we multiply 57.56 here is, or 57.6 here is by 0.509. And then toluene we multiply by 0.033. Then ethyl acetate by some other value. I can't see it right there now, right? And we add them up, and they add up actually to the model sum here of 47, right? And 47 here, this guy here is the sum of this times this, plus this times this, plus this times this. Does that make sense? And then the residual there, this is the mixture signal minus the model sum signal. And this is a terrible residual for the first point, but if you look overall, right, if you look at the entire spectrum, the residuals peak at about plus or minus 300 here, right around this band. But that's about a 10% error at worst, and closer to maybe a 2% error in most other places, 2 or 3%. Does that make sense? So, so it's a short story, basically. I think I might have to make some screen clippings of this to give you more guidance, right? And that's all you're going to do for this exercise. You just answer a few of these questions, right? What are these guys? What's in this row? So let's look at what's in this row, right? These are the uncertainties, right? So 38.7% ethyl acetate, plus or minus about 0.3%. And then 3.3 plus or minus 0.1, and 50.9 plus or minus about 0.3%. Does that make sense? Richard is gone now. Oh no, Richard's back.
I'm here.
Yay.
I do have questions about the uncertainties, though, how you found those.
Yeah. So there's a way to calculate them. I know something about it, but it's actually pretty opaque. So, I mean, what does uncertainty mean to you? I mean, just if you were to put that into words.
The value could be within some specified range, and that's kind of
Exactly. So, like, when we say that acetone is 50.9 plus minus 0.3, what that means basically is that if we increase acetone by 0.1, or actually this is 1%, right? These are 1% changes in acetone. It doesn't change the overall fit very much, you know? Can you guys see what I'm doing here? I'm twiddling this knob that's over acetone. And that changes it changes the model sum and the residuals here. This plot is actually residuals. Oh, I should probably label that. So who can define residual for me? Volunteers? You're going to write on your face with a Sharpie pen.
Oh, Dr. Darrow?
Yes.
Since it's the model minus the mixture, it's whatever is left.
Right. Right. Exactly. So if you look at this spectrum of residuals, you know, what does this tell you?
There's a lot of it.
Yeah, there's a residual for every point in the spectrum, yeah? And the magnitude of the residuals here, let's take this first 650 wave numbers. It goes, you know, it oscillates mainly between about plus or minus 50 here, right? Then there's a little more of an excursion here. And this corresponds to this peak, right? Then there's a much larger excursion here. This is sort of a derivative peak, right? Then there's another peak here, another derivative peak here, etc., right? So if this were a perfect match, what would these residuals look like?
They would be gone, right? It would be a flat line.
Oh, that's an excellent point. Yeah, if it were perfect and the data were perfect, then it would be a flat line, right? I overspoke that one, right?
Okay, then I think what you mean is it's just going to superimpose just very minor.
Right. It'll be small, and it will be one other thing. The other word I'm looking for starts with an R. and ends with an M and has an ND in the middle. R blank ND blank M.
Random.
Random. Brilliant. So this is really reflecting the random noise in the spectra, right? And if all the assumptions for the least square are exactly fulfilled, then the residuals will be just random. So so let me ask you this: are these perfectly random residuals? Aditya?
Doesn't seem like it since many of the residual peaks are lining up with the actual peaks themselves.
Right. So what do you think's going on?
Maybe that.
It's hard to say. It's hard to say. Right? There can be something physical happening, right? If the presence of two oscillators in solution shifts the frequency of one or both, then that will create, probably a bipolar oscillation like this, right? And I suspect this oscillation here is probably 1, 2, 3, 4, 5, 6, probably 6 or more points wide. So this appears to me like it could have to do with some peak shifts. Another possibility is that's optical, has to do with the efficiency of the high resolution spectrometer. So there's a moderately high resolution spectrometer here. It's about 0.1 nanometer, or about 16 wave numbers. So so this could be an artifact either of the ability of the monochromator to work well, or of the interaction between oscillators, and we don't know which one it is. Interesting question, yeah. So what's another question we have here? So here's something that I would like to point out to you. What if I were to take this acetone component and make it 0? I'm going to make this acetone component 0 here. 4, 3, 2, 1. Zero. Now, what do you suppose this looks like? What does this upside down spectrum now resemble?
The one that is on the top graph, it looks like it's a mirror image.
It looks a lot like that, yeah. True. It also happens to look like, let's see here. These labels got kind of messed up, but oops. Right. So this is, let's see what I'm doing here. There's a mixture. There's ethyl acetate. There's the model sum. Come on, you. Ethyl acetate. Model sum. Mixture. Anyway, the point I'm trying to make is that this looks like acetone. It just looks inverted. It looks a lot like the acetone spectrum. So if you remove one of the components, you can see it in the residuals. Right, so let me put this guy back. This is 0.51, right? 2, 3, 4, 5, 1, right? Now let me take out ethyl acetate. Right, so here's more or less what the ethyl acetate spectrum looks like. A little bit more complex, a few more atoms, whatever. You know, it doesn't have this peak in it, right? It's interesting. As this one. So you can play around with this, right? And so if you're ever modeling a spectrum, it's really helpful to plot the residuals, because if you're missing a calibration spectrum, then it will show up in the residuals. Does that make sense? Beautiful, beautiful. Okay, let's see here now. It's point. This guy's got to go up to 0.39. There we go. Where that one I was supposed to be. Now here's the Linast fit. This is the fit that's statistically, this is the best fit that you can get. Like, there is no better way within the constraints of our model here, right? Which is that the mixture is equal to these three things times their respective coefficients, right? There's no way to get a better fit than this. It's one of the beauties of Linast is that there's an explicit best fit here. So anyhow, this looks just like this, right? Because it's, I mean, this is by hand, but this row here, actually here when I make these percents, right? Right? This is 38.7. Oops, sorry. This is 50.9. This is 51, right? 3.3, 3.3, 38.7, 39, right? So these three here match these three here, right? I'm gonna make them a different color, right? So it's sort of more obvious what's going on. Okay. All right, enough of this boring stuff. And so you guys, does everybody have access to Excel or something equivalent? Like you can probably use the Mac thing. Yeah, good, excellent. Or you can use OpenOffice, or you can use LibreOffice, or you can use Sheets, Google Sheets. They all have Linest. So you should be able to do this in any one of those things. And then you can give them back to me maybe in a week or so. So next Tuesday night, I'll expect a flurry of questions. All right. So are there any last questions on the spectral analysis by Excel's Linest? Nobody's going to punch this hornet's nest, are they? Let this one go. Okay, cool. All right. So let's talk about our next paper then. The next paper is right here. And it is surprise today, right? Because I didn't tell anybody it was coming up. I hadn't decided what I was going to do today, but I sort of decided at the last second here. And I decided to use paper that intersects pretty well with my knowledge base, and it's also sort of my interest base. So hopefully it won't be too boring for y'all. But it's a biosensing paper that uses surface enhanced Raman. So and it also uses an interesting way to bring out these spectra, basically to concentrate and enhance the spectra. And so let's see here. There's so what is done basically is sort of zoom in here. Oops, oh no, don't go there, don't go there. Sorry, oops. I just want to come out one or two, there we go. Is that what they did was they made a little cell. This is a flow cell. And it's made out of PDMS, or polydimethylsiloxane. And so it's basically silicone rubber. It's really soft. It's a nice soft rubber. And it's silicone, and you know, they work pretty well. I'm sure they absorb stuff, but you can just sort of throw them away when you're done. So but this is a molded PDMS piece. It's probably I think it's like half an inch in diameter, something like that. They said it somewhere. I think it's or it could be like a centimeter in diameter. But and then there's this well in here, right? So stamped into the PDMS piece, there's a well. And on top of the well, there's a cover slip. You guys following how this works? More or less. And so there's an input here, a fluid input. Then the fluid leaks through this channel. It fills up this well, and then it goes out that channel, right? And I'm sure it just goes right to waste there. There's nothing downstream. This is just to fill up the channel and see what happens, right? And in that channel, that's made of PDMS and covered with a microscope slide, they flow in a solution of gold nanorods. So a gold nanorod is about 15 nanometers in diameter by about a couple hundred nanometers in length. So, and there is on the order of 10 to the 8th of these rods per cubic centimeter. So let's, okay, we'll do a calculation on that soon enough, right? Then what they do is they flow this dilute solution of rods in. And then what they do is they turn on a piezoelectric actuator underneath, right? So this is called a transducer. And what it does is it shakes. And it shakes this thing at about a megahertz. So it creates this intense acoustic wave. You know, it's creating compression and rarefaction waves in the glass, in the solution, in the rubber, and in the steel, right? And the idea is that if you do it at the right frequency and the right amplitude, then you can cause the contents of this cell to flow to the center. and then the solution will be pushed away, and the rods will accumulate at the center. And then by accumulating the rods, what you're doing is you're collecting chemicals from around in the cell, and you're concentrating them in the center, where you can focus them into the beam of a helium neon laser, and then irradiate them and collect the radiation and look at the Raman spectrum. So this is a Raman microscope application, and that's not really our focus here, but I always love how it's kind of an easy setup in some ways, right? Because what you do is you direct your laser beam right down the barrel of this microscope objective, and you get that guy to focus right in the center of this cell here, right? And then the backscattered radiation is collected by the very same lens, and then it is refocused onto a beam splitter, and then that beam split radiation is taken off to the spectrometer. So that means that the laser focus and the point at which you collect the radiation are the same. So so you never have to try to align the optics of what you're looking at, you know? You just have to get it focused, and then boom, you're seeing the scattered light from the laser focus, right? It's a fucking miracle, believe me. Sorry. It is. It's a miracle. It makes things so much easier. So so the laser comes in here, and it backscatters out, and you collect that radiation, and you chop out the 633 from the helium neon laser, and you just look at the Stokes side, and you can see the scattering spectrum of they decorated these rods with DNA, right? And this is basically it's a proof of concept of this type of thing, right? So all right, so that's so let me read the advertisement, aka the abstract here, right? Enrichment and enhancement, right? Enrichment means, what they're meaning is that they're concentrating into the center of the cell. Enhancement happens because of the interaction between the rods and the radiation from the laser. That radiation excites a plasmon in the rods, and the plasmon leads to surface enhancement of the Raman. And the surface enhancement takes this extremely weak phenomenon, which is Raman scattering, and multiplies it typically by 1 million to 10 million, maybe 100 million fold in some cases. And so these rods, these gold nano rods, are basically like antennas for the radiation that comes in. And they focus it probably at their ends, and then the ends of the rods light up with Raman signals like you wouldn't believe. So that is enrichment and enhancement, right? Enrichment is from the magic of the ultrasonic transducer here, the sonicator. I might call it a sonicator horn sometimes, because they're basically big jewelry cleaners, you know? This type of thing is used, you can dip it into water, and the water will become agitated with its very high frequency, and it will just scrub the surface of whatever's in there. So you can put soap and water in there and put the sonicator horn in, and it'll clean things up very nicely. But in this case, they're using it to create a pressure wave in the cell to drive the nanorods to the center. I'm not sure how that works. But the acoustic aggregation, right? So acoustic induced aggregation, really. So the acoustics concentrate the nanorods, and then aggregation is actually a phenomenon where the repulsive interactions between the rods, between the similarly charged rods, are overcome, and then they stick together. Right? There's a colloidal force that keeps them apart, which when overcome will allow them to stick together. And in free solution, these rods will not aggregate. But if you put them into this ultrasonic field, then they'll have higher velocity and they'll overcome their repulsion and they will aggregate. And then the gold nanorods migrate to a pressure, they say a node here. And I am absolutely convinced that they're using that word wrong. Because a node is a 0 point in the field. And all of their simulations and everything are showing that the center of this is a high point in the field. So, whatever. I mean, they obviously know more about this than I do, but it's translated from Chinese, and I think there might be some, anyway, it's a pressure antinode, really. And it takes a few seconds to concentrate these guys in here. And then they can see the DNA that they decorate these nanorods with in the Raman signal. And so they use they're detecting complementary DNA at very low concentrations in this cell, right? And 10 to the minus 13 molar times 10 to the minus 6 liters, right, is around their detection limit. So let's do a quick calculation here. I actually have to get my stupid thingy up and going here. Okay. So this may cause you some consternation, and it causes me consternation, right? I'm not sure how we may or may not resolve it. But this is one of the ways that we caught the Saylor article on porous silicon about 15 years ago, when they got retracted from Science. From Science, that's the premier scientific publication that there is. And his student made a mistake. They published it. And it looked really sexy, but it was wrong. Anyway, he was embarrassed, but he's still a kick-ass scientist. Trust me, he's an interesting guy. So they're talking about a concentration of the DNA at about 10 to the minus 13 molar. That's their detection, right? 10 to the minus 13 molar, right? Oops. Come on, Roger. 10 to the minus 13 molar, right? And a volume of the solution of about 10 to the minus 6 liters, right? So the number of moles of DNA will equal 10 to the minus 6 liters times 10 to the minus 13 moles per liter will equal approximately here 10 to the minus 19th moles. So if that doesn't surprise the shit out of you, I don't know what would. Right? So 10 to the minus 13 moles of DNA. That's the entire volume of this cell, right? Now, it could be that they flow a bunch of stuff through, but I don't think so, right? Because of the way they do this experiment. So it could be that they incubate the rods in a large volume, but I'm not sure about that either. Because they don't have very many rods, they don't have so much DNA, right? They're talking about 10 to the minus 13th moles of DNA that they're detecting, right? So 10 to the minus 13 moles of DNA times 10 to the 23rd times 6 per mole is equal to 10 to the 7, 8, 9, 10. About 10 to the 10 DNA molecules. So about 10 billion. In this cell, right? Okay, that might work. So now let's see how many nanorods they have there to collect them. So you have to dig just a little bit in here, and we'll read this guy more carefully here. Well, nanoparticles, about 5 times 10 to the 8th per microliter. Oh, that's way concentrated. Okay, so and the number of nanorods is approximately 5 times 10 to the 8th, or 500 million. Right. So we've got about 20 DNA molecules per nanorod. So we've got 10 to the 10th over 5 times 10 to the 8th is about 10 over 5 is 2, right? Times 10 to the 2. That's 200, right? 200 DNAs per nanorod. So that gives us an idea of what sort of analytical challenge they're up against. So if I were reviewing this article, I would have done this calculation early on just to see, like, is this possible? Are they did they make a mistake and where they couldn't possibly have seen it? But who knows? It's possible. It's possible, right? And this is given at 10 to the minus 13th molar, right? So now, if this is concentrated down by a factor of 100, right, by the ultrasonic field, then this could be 10 to the minus 11th molar locally, right? Like if the rods gather up all the DNA and they bring it to the center, it might be 10 to the minus 11th molar locally, right? So so 10 to the minus 11th molar locally. So so let's talk for a moment about gold nanorods and their plasmonics, just to get an idea of, so we can get an idea of what a SIRS signal is, right? This is, they just start using the acronym SIRS. I don't think they ever define it, right? Detected by SIRS here. blah, blah. Ah, yeah, here it is. It's a surface-enhanced Raman scattering strategy, right? Surface-enhanced Raman scattering. So we didn't talk about SIRS, did we? Does anybody remember talking about it? I don't think so. Okay. So SIRS is a way to enhance the signal for the Raman signal for certain molecules by factors of 1,000,000 to 100 million. Right. So the way this works for gold nanoparticles, let's start with gold spheres. I'm sorry I don't have better graphics, but you can make colloidal spherical gold, which are on the order of 10 nanometers in diameter, by reduction of gold salt with sodium borohydride or scorbate or citrate, these types of things. And what you'll get is a red solution. You put the ingredients in here, put tetrachloroauric acid, and you put citric acid, and you got some water there. And what will happen is that this solution will slowly, you stir it. Sometimes you boil it, make it go faster, to get more uniform particles, right? Is the solution will turn red. It's actually a wine red color. And that color comes from the interaction of these small spheres, these small metallic spheres with light. And what happens is that the EM field of the light comes along. It will induce a dipole moment in the free electrons in the sphere that is resonant with the light frequency around, it's around 400 nanometers. And so this resonance, it's a broad resonance. Around 400 nanometers. And this creates an intense red color. Which is due to what's described as the localized surface plasma. Okay. So I have to take a breath now. We have to talk about a distinction, which I'm starting to see in a little bit of a new light right now. And there are molecular states and quantum states in like semiconductors where you have a band gap. And these quantum interactions, they absorb photons completely, right? So the photon will interact with them and be completely absorbed. And then there are much more classical interactions between light and matter, where the light is not always absorbed. Sometimes it's absorbed, sometimes it's scattered. And Raman is actually one of these classical-like phenomena where light is scattered, but the frequency is shifted a little bit by the vibrational quantum. was sort of in between there and straddling the two worlds, scattering and quantum mechanics, right? So those phenomena are normally pretty weak. Things like Rayleigh scattering, and they often are traceable to the interaction of an electric field with the polarizability of an atom or molecule. So it's the dipole moment of the light and the induced dipole moment of the atom or molecule, which will cause Rayleigh scattering. And the fact that that polarizability is modulated by vibration gives rise to Raman scattering. Now, for these metal nanoparticles, they have a further interesting, classically described interaction with light that's very intense. And that classically described interaction is called a plasmon. You know, it's a classical interaction. They have to give it the ON just to be frickin' fancy. Honestly, it's a crime. And I should have. There's a guy named Heinz Rather who wrote the book on this originally in the 60s, and it's just a crime because it's a classical phenomenon. But the classical phenomenon for these spheres means that the absorption versus wavelength, like it kind of looks like this, and this is about 410 nanometers. And so there's a lot of light out here in the red and the near IR that's transmitted, which makes these guys wine red, right? So now it was discovered by accident that when molecules adsorb to the surface of these resonating particles, for example, this is supposed to be a nitrogen here. This is 4-mercapto. Pyridine. Right? When a molecule adsorbs to a 10 nanometer particle, you know, and this covers a range, right? It can go between, you know, a couple nanometers and maybe 50 nanometers, right? When a molecule adsorbs there, there's an enormous, freaking enormous increase in the Raman scattering cross section of this molecule. And there are still, you know, people fighting about why. What's the mechanism? You know, what underpins this? You know, and there's probably a bunch of things, right? One is there can be electronic resonance between the particle and the molecule, like partial electron transfers between hot electrons and maybe electronically excited molecules, who knows? So the surface enhancement of the Raman signal picks this very, very weak signal up out of the noise and can make it literally as intense as the fluorescence of a good fluorophore, like a rhodamine 6G. And this has been demonstrated. It's been demonstrated in interesting experiments, which in which you can't always control the exact geometry and things, but you can sort of go fishing and you can find single particles lighting up single molecules for which you can get the Raman spectrum of a single gosh darn molecule. Right? So you can get single molecule SIRS. You know, you use a microscope, etc., but it's pretty damn impressive. So surface enhanced Raman comes from the plasmon field, interacting with the molecule, and probably electronic effects, and many other things. Right? So I'm not a physical chemist, and this is one of the big reasons why is I don't really have a dog in this fight. So I'm just going to throw out all these things, and you know, one or more of them may be right. I'm not really sure. I would love to find experiments that we could do to sort this out, but honestly, that's being done by smarter people than me. So, but the thing is that this effect goes to 10 to the 12 to 10 to the, 10 to the 6 to 10 to the 12 fold increase in the Raman scattering of the pyridine. Right? So, you know, basically the fact that it's adsorbed onto this molecule and you're mixing this plasmonic state with this molecular state means that a lot of the normal selection rules break down and you get 1,000,000 times more light out through the Raman channel than you normally would. So, okay. So, but this is idiosyncratic, right? Not all molecules do this. Right? One excellent exception is water, right? Water is a solvent in all these damn things, and you never, ever see a SIRS signal for water. Go figure. It's like God playing games with us, you know? You know, like we're all excited because we see this huge pyridine signal, and we write papers on it, and somebody says, why don't you see water? We're like, holy fuck, I never thought about that. It's 55 molar, you know? It's hugely concentrated, it's everywhere, and there's no signal from it at all. You know, it's adsorbed to the surface as well. So anyway, so there's an idiosyncratic effect there, right? And then people over the years have found that gold nanorods are very good surface enhancers. Right? And so basically you make your gold particles in this solution called CTAB, which is cetyl trimethyl ammonium bromide. And this will cause these guys to grow into a rod. So you take a particle, a seed, and then you grow it, and you get rods. And they are roughly, and you can do this such that you get, 15 nanometer diameter and 50 nanometer length, etc. And what appears to be the case is that these rods will interact with radiation in such a way that they get a strong electric field at the ends. And so you'll get a lot of enhancement. Then there's another trick, which is aggregating the rods. Which adds, another 100 to 1,000 fold increase in the Raman cross section. So, bringing this back to what these guys did, they have a way to take this roughly 1 microliter well and focus a collection of nanorods and cause them to aggregate in the center. And then they can look at the molecules that are scavenged by the DNA fur that they put onto the nanorods. All right. So, who has questions or complaints or a desire to stick a fork in my eye? I think Hikun wants to stick a fork in my eye. That's all right. I would want to stick a fork in my eye. I don't know how to see. I don't know how to teach. It's supposed to be all participatory and everything, but I'm just too damn lazy, I guess. So, let's see. Blah 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 blah. Here, let's read up here. So, they made an ultrasonic device. They made gold nanorods with CTAB. They modified them with DNA, right? And then they added some rhodamine 6G. Oh my gosh. That's interesting. Rhodamine 6G, and then I see. This is rhodamine 6G and unmodified gold. And then they added DNA modified gold here. And they added target DNA, right? So this is a trick that's used by analytical chemists when they want to get credibility in the biochemistry world. Amino acids are difficult to find by a lot of methods. I mean, they don't have good ultraviolet absorption, and they're hard to find by Raman and SIRS and all these other things. But the nucleobases, adenine, guanine, thymine, cytidine, all these guys they have good Raman cross sections. So, you know, DNA modifying the nanorods is an interesting and, you know, sort of it's gonna work approach here, you know. So there's nothing left to chance here in that sense. So so what they did was they put mitochondrial RNA in into this cell, right? And then you know, and then they have complementary DNA on the nanoparticles, and they see if they can detect them, right? Right? So so I think that's about enough for today. Are there any questions about this so far? No, I just threw it at you, so I don't expect you to, like, you know, have any idea what we're, you know, any like deep insights or anything. I'm just sort of like throwing it out there. This is kind of a cool one here, right? Here's a TEM of the nanorods. I love this, man. It's like, it's pretty cool that they can get a TEM like this, you know? And you can see that the nanorods are different colors based on their orientation in the electron beam, their crystallographic orientation. That's kind of cool. And then here is a very weird finite difference simulation of the acoustic wave in the cell. Right, they've got a horn, they've got PDMS, they've got fluid, and they've got this cap here, right? And they did a bunch of simulations, right? And they say there's a node, there's a single node at the center, but that's not a node, that's an antinode. Because this is a high pressure point, right? And then there is a node, an annular node here, right? And then there's another node at the edge, right? And the fact that this is red and this is blue means that they have only one phase. This simulates only one phase of this acoustic wave, right? Because there's no way this could be RMS and have a -2 times 10 to the 4 Pascal region here. I just don't think that's possible. So I think this is one phase, and that there's a high pressure here and there's a high pressure here. There's two nodes. And it's basically an oscillating pressure, right? The pressure is going high, low, high, low, high, low, high, low, right? But they didn't seem to, it's kind of strange with the way they wrote this. They didn't mention anything like you know. But I don't know. Trust me, if I could write in Chinese, I would be ecstatic. But I couldn't even say my name in Chinese. So this is an amazing accomplishment, whatever the little quibbles I have here, right? About node or antinode, and whether this is an RMS pressure or whether this is an absolute pressure or whatever. I suspect that this is one one phase of an absolute pressure, like peak there, and then a valley there, of an inward going pressure wave, right? But you can put this. This is the little cell filled with nanorods, and then in 25 seconds you can get them to collect in the center, and that is friggin' cool, So you might be able to do this electrochemically, but this is just really cool. You can do this in the ultrasonic field, and you can use larger concentrations and make a bigger blob, if you need to. But I don't really know about this, how to critique it or anything. That's fine. But then also they have a TEM of the center region here, and it shows a lot of blobs. It shows round ones and rods and stuff. And this is absolutely to be expected. It's perfect for enhancement, because normally you get a mixture of rods and spheres when you make these particles. So this is sort of the exception, right? And this is more the rule, where you get a whole mess of different stuff. So anyhow, time for me to shut up, and I will make the assignment for you in Canvas. You can download it and jump on it whenever you like, and then don't wait till the last second to start asking me questions, because I will take them on you by Zoom, and then we'll publish what we learn, and so the rest of y'all can learn by those examples if you want, or we can just do it privately, whatever you want. Alrighty, guys. Thank you so much for your attention. Thank you, Richard. Thank you, Aditya. Thank you, Hikun. Thank you, Dan, in the Horsehead Nebula. Thank you, Adam. I'll see everybody later.
Dr. T.
Thank you.